All right, so another thing that we can talk about here too is the graviton. And this is the hypothetical elementary particle that mediates the force of gravitation um, and the framework of the quantum field theory. If it exists, the graviton is expected to be massless because the gravitational force appears to have unlimited range, and then also must be a spin 2 boson. So it's interesting. I mean, just seeing our limitations here, right? I mean, this is hypothetical. We're using the standard model. We confirmed the Higgs boson a few years back, but there's still a lot of unanswered questions. And so this very well could change in the future as we continue to dive into particle physics.
Now, the other force that we want to definitely talk about is the electromagnetic force. The exchange particle is a photon. You have the gamma ray, symbol here representing for a photon, and that's the exchange particle with the electromagnetic force. Okay, now with confinement, quarks only exist within hadrons. You can't have an isolated quark. I can't just hold an up quark in my hand or something like that, right? There's many things wrong with that, but you can't just isolate a quark on its own. Now, what's interesting about the, like a meson, for instance, if you had a quark and an anti-quark, right, and you're trying to separate them, they are not going to want to separate. And it actually turns out the further you try to separate those, the more energy that it's trying to hold to keep them together. It would take an infinite amount of energy to actually separate them. And so you can't separate them. You have to have those individual quarks. Now, the standard model of, is including all the things we've been talking about: quarks, leptons, the exchange particles. This is defining the standard model, and we have really good experimental evidence for this. Now, the missing link all this time was the Higgs particle, and what the problem was with the weak force. And so, what happens with the weak force mathematically? It showed that that there is the photons, the W and Z particles of the weak force do not have mass. However, the W and Z bosons here, right here, okay, actually have a lot of mass. They have a lot of mass, and so that's a problem. And so they made the theory that there must be this Higgs field, and that this Higgs boson, this Higgs particle, must be here. And so they thought that really that Higgs particle is responsible for, through its interactions, that because of the Higgs particle and the Higgs field, we do have the W and Z bosons that operate, like the way that the standard model looks at. And so there's a really helpful analogy that looks at this. And it turns out in 2012, they did find it, and they measured it. They were actually able to get it at the Large Hadron Collider. It was predicted within the standard model a long time ago, but they finally were able to discover it. Now, this analogy hopefully will be helpful for you as you try to picture this. Let's say you're pulling a ball through the air, right, with a force. We know F equals ma, right? But we know that air is a fluid and it makes it slow down, so it can't be quite as fast as it normally would be. So that counteracting force makes the acceleration smaller than we expected, and that's kind of like if we had a ball that had more mass, but we didn't have air resistance. It would have more inertia, right? And so, it's showing that, that ball, as it goes through the air, right, would have some of that air resistance, but it's just like if we had no air resistance with a little bit more mass. That's roughly how the Higgs works. And what I'm going to do is in the links here, I'm going to give you this video that you definitely need to watch, and then I'm going to do the other one, hopefully with the standard model that I'm going to include in there as well, that give you a pictorial picture of what's going on with this, and that'll be good.